of all, a very good morning to everyone present in the auditorium. Thank you so much for giving me this opportunity. I was here sometime around last month participating in Sci-Fi, and I'm back today for this wonderful event. And to begin, my name is MAITREYO BHATTACHARJEE. I am currently a sophomore undergraduate student at the School of Mathematics and Computational Sciences, Indian Association for the Cultivation of Science, Kolkata. And the topic of my today's presentation is based on the prime numbers, their history and the mysterious distribution. To give a brief background about myself, I am an analytic number theory enthusiast and I do some work on that. Yeah, so let's begin. So first of all, I would like to acknowledge the Department of Mathematics here at Untitled for giving me this opportunity. My sincere thanks to the Mathematical Association of American Archive for giving me the permission to use numerous resources which I have used while preparing the slides and also doing my research. And of course, thanks to my parents for everything. Yeah. So to begin with, literally every one of us, be it a science student or not, are introduced to the concept of numbers right from their childhood. The numbers, as we all know, we first study the concept of natural numbers, which are 1, 2, 3, 4, 5, and so on. And to visualize natural numbers, we have so many things around us. I mean, literally in the hall itself, there is one laptop present over here. There is X number of people, or there are two water bottles present in front of me. And so, after we are introduced to numbers, mainly the second concept to which we are introduced are the concept of prime numbers. So, what is a prime number? A natural number n is called a prime number if it is divisible by itself, the number itself, and 1, and no other proper divisors. And as I have used a notation over here, which is not that much standard in modern mathematics, but I have denoted a set of all prime numbers by the capital letter P. And as you can see over here, the prime numbers form a subset of natural numbers, which are in turn included in the integers, the reals, and the complex numbers. So this forms a nice embedding. Yeah. So the history of prime numbers dates back to the Greeks, And apart from their dominance in pure mathematics, the various disciplines of pure mathematics, they are also extensively used in computer science and in the study of RSA cryptography systems. Some part of cryptography system was coincidentally covered by my two previous speakers. So first we will see a graphical representation of prime numbers. So one fine morning in some place in Sweden, there was this mathematician, Stanislaw Ulam, one of the most celebrated mathematicians of the last century. And he was actually attending a lecture and he felt very much bored. And he had a paper and pen in front of him and he was just wondering what to do in the coming 1 hour or so. So he started writing all the natural number system and marking all the prime numbers. And as you can see over here, we have, after a certain number of time, and if we increase the number of natural numbers considered, then we can see a very special kind of spiral in them. As you can see in this picture is nothing else but a zoomed out picture of this kind of picture. And here we have a large number of natural numbers, and here we have a very small number of natural numbers. And if we mark only the prime numbers, we can somehow exhibit some very special properties and patterns among these. And later these were analyzed mathematically and there are some polynomials for the same. But vaguely speaking, we can see some strange patterns which is reflected in this picture also. And this was basically published by Martin Gardner in one of the journals of the American Mathematical Society in 1964. And so this is a very nice way to visualize the prime numbers. Moving on to next. So previously, we had basically considered the prime numbers in a very linear fashion, right, going from left to right. Now, we have all heard about a coordinate system and the polar coordinate system. What if we focus the prime numbers on the polar coordinate system instead of the Cartesian coordinate system? So if we do that, we see such kind of structures. It's dense in the beginning and it gets sparser and sparser as it goes down. And this is a much zoomed out picture and you can see there are strange patterns among them. And yes, this is all the whole picture. This is a plot up to 5,000 and this is up to the plot where we considered 50,000 primes. And this picture I have taken from the LinkedIn post of the Formats Library. It's a beautiful resource for learning mathematics. Yeah. So now, what can we say about the cardinality of the set P? So is it finite or is it infinite? Cardinality is one of the most basic concepts which we come across in our basic set theory courses. So this was proved by Euclid and this is a very famous theorem that there are infinitely many primes. And the proof sketch, I am very sure that almost all of us are familiar with the proof sketch, but I will just repeat it. So we contradict and say that there are a finite number of prime numbers, and if there are finitely many prime numbers, there must be a largest prime. So let that be denoted by Pn. And then we define another quantity, big P, which is defined by the product of all the prime numbers up to Pn and plus 1. And so we can of course do that because prime numbers are nothing else but natural numbers. And then P is assumed to be the largest prime. And then we basically test which prime can divide P. And by doing this, we will come to a contradiction that there must exist another prime which is not equal to any one of P1, P2 up to Pn. So the primes cannot be finite in nature. And this is a very small proof, but one of the most beautiful proofs, and is a much celebrated proof. And later on, by numerous studies by mathematicians from various backgrounds, there have been not less than 183 many proofs of this theorem. And I have just cited the paper of Untitled, which is a very nice survey paper which contains the links to all the proofs and various backgrounds behind them. And there have been various techniques involved in proving them. One is involving topology, more specifically point set integer topology, which was used by Furstenberg in 1995, so much celebrated result. Furstenberg, as you all know, is the 2020 Apple Prize laureate in mathematics. And very recently, there has been another proof using fractals, so it's quite beautiful and quite elegant. Yeah. So prime numbers, in some sense, can be considered as atoms of integers. Like in chemistry, we have learned a similar concept of molecules and atoms. So how is that? So this is a fundamental theorem of arithmetic which was known since antiquity, that every integer greater than 1 can be represented uniquely as a product of prime numbers up to rearrangement. So as an example, we see that if we consider any composite natural number, 1200 or 104, you can take 100 or 2000 or 2 million or anything, where it can be broken down in terms of prime numbers. And from this I think you can understand or get an idea that why I am referring to the primes as the atoms. Just like in a very complex organic molecule, there is a small number of atoms present over here, and this special organic projection which I used over here to get the corresponding idea. And this is a very famous and one of the most basic theorems in number theory. Yeah. So now I come to the main point of the presentation, and this is one of the most important topics currently being studied all around the world. And over here, we will study the gaps of the frequency in which the prime numbers occur in the natural number prime. So let us define a quantity known as Gn as difference of the two consecutive nth prime numbers. This is referred to as nth prime gap, Pn plus 1 minus Pn. Now, one very basic but important remark about this is that this Gn can be made any big which you want. And this can be successfully demonstrated by taking this particular sequence. N factorial over here denotes the usual factorial notation used in mathematics. And if you take this sequence, each of the numbers present over here is not a prime. And the proof is very much simple because you can take each of the numbers common from here. 2 can be taken common because n is greater than 2 over here. And thus you can get arbitrarily large sequence occurring in the natural numbers. None of them are prime. Now, the main question in mathematics is to find some finite bounds on the least gap of consecutive primes which occur infinitely often. We know that there can be gaps which can be as large as any possible value which we can imagine. But the question which we want to study is that can the gap be very much minimum? Like, can there be prime gaps of 7 which occur infinitely many often, 10 which occur infinitely many often? This is the main question which is the focus of the study. And the answer is yes. But the study behind this was a huge one, and this was successfully done in 2013. I have quoted the date also. So this mathematician, Yitang Zhang, who was then a lecturer at the mathematics department at the University of New Hampshire, proved a breakthrough result in analytic number theory. This I have stated directly from the paper, but this basically means that this number, 7 into 10 to the power 7, the prime gap attains this value infinitely many often as n goes to infinity. So this is a very important factor. So basically the twin prime conjecture, which we will see in a few moments, it tells that the value of 2 occurs as a prime gap infinitely many often. But as we know in mathematics, when we are trying to reach any goal, it's often very much impossible to reach that goal directly. Instead of that, many times we come across some other results, then we try to simplify that and make it more fine using some advanced techniques. And after this, there was a huge collaborative efforts from Maynard. Maynard is a mathematician at Oxford, and he's a probable field medalist in 2022. He gave an alternative proof of this statement, and there was a collaborative project set by various mathematicians around the world, known as the Polymath project, which the basic aim of the project was to reduce this quantity, this particular quantity. And after lots of study, this has been successfully reduced to 246. And if we assume another conjecture in mathematics, it's a conjecture, not a theorem, it's known as the Elliott-Hilbert-Stone conjecture, then this bound can be reduced to 6. And the current area of study focuses on reducing this bound to 2. Yeah, so the target is to reach, as I told you, the twin prime conjecture. There are infinitely many primes, P1 and P2, such that mod of the difference of P1 and P2 is 2. This is a bound of 2. We want to make the bound as small as possible. Now, I will discuss some two very famous theorems related to the primes. This is known as the Green mark. There are two landmark theorems in this area. The first is known as the Green-Tau theorem, which was published in the Annals of Mathematics in 2008, and which says that the primes contains arbitrarily long arithmetic progression. This means that if you pick any natural number k, let's a very basic example will be 3. We know that 3, 5, and 7. These are 3 primes, and these are an arithmetic progression. So what Green and Tau prove is that if you take any particular natural number, let's say 10,000 or 2 million or something else, then you will get an arbitrary arithmetic progression consisting of only prime numbers which has k many terms. And the proof is an extension of the Maynard theorem, which is again another very famous theorem in arithmetic combinatorics, used frequently in many other areas as well. And here is archived into the paper. And very recently, a very important theorem proved by Maynard imposes a kind of digit restriction which can occur in the prime. And let us see what the theorem says. It says a very interesting fact. So you pick any particular digit. Digit, as we all know, varies from 0 to 9. So let A0 be a digit you pick at random. Then this theorem claims that there exist infinitely many primes which does not have this A0 in the decimal expansion. Like if you pick 5, there occurs infinitely many primes which does not have 5 in the decimal expansion. Right. So, and as we all know, the Riemann hypothesis is one of the Clay Mathematics Institute on major unsolved problems, and this was basically formulated by Riemann in his 1859 paper. And the hypothesis says something else, but the beauty of mathematics is that it is deeply connected to the distribution of prime numbers, and especially the prime number theorem. So basically, assuming the Riemann hypothesis, we can say a lot of things, and I mean over 500 papers have been written which assume the Riemann hypothesis and does some beautiful stuff. So the major factor which comes into the play is the Riemann zeta function. But the thing is that mathematicians haven't been able or successful to prove the Riemann hypothesis, although there have been numerous progress. And one very important tool used by analytic number theories frequently is the subconvexity tool. And using this, sometime around last year, one person known as Paul Nelson of Caltech posted a paper in the archive which was about 250 or 260 pages long, and it made a subsequent progress towards proving this Riemann hypothesis. And this was, I have just quoted the Quantum magazine article of the same. It's a very beautiful article, and this basically shows that how difficult mathematics can be, and it basically involves ideas from a huge number of areas, not only analytic number theory, like algebraic number theory, representation theory, and so on and so forth. And
by the way, sorry to interrupt, 30 minutes is over, you have 2 minutes to complete.
Yes, just wrapping up. This is a major achievement of 2021 in mathematics. And lastly, the talk would be left incomplete without mentioning a few people who are working extensively in this area. This is Yitang Zhang, who was the first person to make a huge breakthrough in this area by establishing the bound on the gaps of primes. And this is, of course, Terence Tao and Ben Green, who proved the major result of the Green-Tau theorem. And this is Paul Erdős, and he has been instrumental in this field for a long time. And he has established a lot of conjectures relating to the bounded gaps between primes. And this is basically another professor from San Jose State University, and his results were used by Yitang Zhang in successfully establishing the Zhang's theorem. And this is James Maynard. He is one of the world leaders in analytic number theory and this field especially, and he is currently working in this field to reduce the gap to 2. And it is widely believed that it will be achieved in the coming decades or so, or we can hope for that. And I will basically end by quoting this very nice survey paper which was written for IC 2018 by Maynard himself, where he was the invited speaker. And this can be seen for very much useful references and a historical saying of what has occurred in the last few decades in this field. And yeah, so by this I would like to end my presentation, and thank you so much for the attention.